This session is about finding the solution set to a linear inequality in one variable. There are three ways to show the solution to a linear inequality in one variable. Three ways that we're going to discuss are graph on the real number line, interval notation, set builder notation. Sometimes easier to write the second or the third method if we graph the solution first. In graphing a solution, we want to show where on our real number line our values of x are that make the linear inequality true. About graphing on a number line, we use symbols to indicate if we are including a point or if we are not including a point. If we want to include a point on the number line, we use square brackets. If we do not want to include a point on the number line, we use regular parentheses. You can check your proposed solutions. For example, we want to graph the inequality x greater than 2. You start out by drawing a number line, finding your point of orientation, labeling it 0. This inequality is about 2, so find it on the number line and label it. And then decide to the left or the right of 2 will be numbers that make that inequality true. Well, you can choose one or you can check it. So suppose I just checked to see if it was x was greater than 2 was to the right. All I'd have to do is find a number to the right and put it in there. The graph above shows us that the solution is all x such that x is bigger than 2. The curved parenthesis means the numbers to the right are in our solution set and that we do not include 2 as part of our solution set. You can check your proposed solutions. I began to allude to this a moment ago. I said if I just chose the numbers to the right, I could choose a number. Well, here I'm going to choose 3, for example. Well, is 3 greater than 2? Yes, it is. Therefore, you do have the correct solution set. So how do you go from graphing to interval notation? First, you need to know a couple of symbols. This is the negative infinity symbol. The one below it is the positive infinity symbol. But typically we just refer to it as infinity. Another way to say x is greater than 2 is to say that the solution set is all those numbers greater than 2 up to infinity. However, you can never reach infinity. Therefore, you can never include infinity. So we never use square brackets with minus infinity or infinity. We use only parentheses. So, if I wanted to talk about all real numbers, I would write open parenthesis, negative infinity, comma, infinity, close parenthesis. Another example, x less than or equal to negative 2. I would begin by drawing a number line, finding my point of orientation, labeling it 0. It's about negative 2, so find negative 2 and label it on the number line. And then decide where are those numbers smaller than negative 2 or possibly equal. And I think they're to the left. So I draw a square bracket and I draw an arrow to the left. And I take a number perhaps that's to the left, like negative 3, put it into the equation. Ask, is negative 3 smaller than or equal to negative 2? And sure enough it is, so I feel pretty confident I have the right set graphed. And I can even put negative 2 in there. Is negative 2 less than or equal to negative 2? Well, it's equal to negative 2, so therefore it has to be part of the solution set. And again, that's why we use the square bracket. And in interval notation, since x is smaller than or equal to negative 2, any x to the left can be included, so we call that negative infinity. So we have open parenthesis, negative infinity, comma, negative 2 with a square bracket showing that 2 could be a solution. How about a compounding inequality? Negative 5 less than x, less than or equal to 8. I like to think of that as x being trapped between negative 5 and 8 because it makes it visually easy for me to graph it. But you can always just take it a piece at a time and say, okay, I want x that's bigger than negative 5. So again, you start with your number line. You find a point of orientation, label it 0. I know this is about -5, so I find it on the number line, and I label it. And I know it has to do with 8, so I put 8 on the number line and label it. And now again, I say, where is x bigger than -5? Well, it ends up that it's to the right of -5. So I draw an arrow saying I'm going that direction. Then I look at x and I say, where is x smaller than or equal to 8? Well, that's to the left of 8. So I draw an arrow going that direction. And arrows on lines mean they go forever, or at least until they meet. And so this indicates that my solution set is in between -5 up to and including 8. In our previous examples, we showed how to graph the solution set of a linear inequality as well as interval notation describing the set of solutions to the inequality. The third method is set builder notation, which can be easily obtained from any of the first two methods. Let me show you how. For x greater than 2, we write this right here, and it reads, the set of all x, such that x is greater than 2. The curly brace, right here, says the set of all. The x simply says x. The vertical bar says such that. That's just mathematical jargon. And then x greater than 2, well, that's what we're trying to show, just fits in there, and we close it off with another curly bracket. How about x less than or equal to -2? We know in interval notation this reads as -infinity, 2, include 2. But in set builder notation, we would write, again, the set of all x, such that, and here it is, it's sitting right here, what we were looking at to begin with, x less than or equal to -2 with closed curly bracket. And finally, how would we write the compound inequality? -5 less than x less than or equal to 8, which again, in interval notation is open parenthesis -5, 8 with a square bracket closing it. So in set builder notation, pretty simple. It's the set of all x, such that, notice what's in here. What's in here is what we were supposed to graph. So it's already set up for us. We simply want x to be bigger than -5 and less than or equal to 8. Close it off with a curly bracket. So hopefully this has shed some light on the three methods for graphing linear inequality solutions. Oh yeah, by the way, the end.